All right, let's go ahead and get started. I want to welcome you back to Unit 8. We've been talking about the mole. This is a number, a rather large number, in fact, 6.02 times 10 to the 23rd. In fact, it's unimaginably huge, and it describes atoms or molecules or very, very small particles. There really isn't much sense as talking about a mole of bananas or a mole of tennis rackets or a mole of ping pong balls because, frankly, there just doesn't exist that many of those items on the planet. So we want to talk about a mole of something that's very, very small. Now, in this problem, we're going to be looking at something called the empirical formula. So I think it's a good idea for us to take a look and review actually what we mean by empirical and molecular formula. So let's start with empirical formula. What do we mean by an empirical formula? Well, we mean the simplest whole number ratio for the formula. So for example, if I have H2O, that's as simple as I can get. 2 and 1 are the whole number ratios for hydrogen and oxygen respectively. I can't get any lower without making one of those two a fraction, right? So H2O is the empirical formula. How about this one right here? We have CCl4, that's carbon tetrachloride. That's a 1 to 4 atom-to-atom relationship. So that's the empirical formula. Now let's talk a little bit about the molecular formula. What do we mean by the molecular formula? Well, the molecular formula is the way that a molecule occurs in nature. So, for example, there's this molecule called ethane. I'll write the formula for it. It's C2H6, just like that. And that's the empirical formula for ethane, right? Excuse me, that's the molecular formula for ethane. But if I wanted to reduce that to the lowest possible terms, I would divide both of those by 2, and I'd get this number, CH3. Okay? Now, there is no compound CH3, right? So it's the empirical formula. It's the simplest whole number ratio, but it doesn't exist. The compound exists as C2H6. So again, the empirical formula is the simplest whole number ratio. The molecular formula is the way that it actually exists in nature. And frankly, many times the empirical formula is the molecular formula. For example, H2O, the empirical formula, actually exists as H2O. It's not H4O2, for example. It's H2O. So the empirical formula is the molecular formula as well, sometimes, but sometimes not. All right? Okay, let's take a look at this example and work our way through this now that we have a little bit better understanding of what we mean by empirical formula. Here's what it says. It says analysis of a compound yields the following percent composition. So this is compound, and it's composed of 6.64% lithium, 1.92% hydrogen, 29.8% phosphorus, and 61.6% oxygen. Folks, if you add those up, they should add up to 100%. Now, we're to calculate the empirical formula, the simplest whole number ratio of lithium, hydrogen, phosphorus, and oxygen. How do we do it? All right, in this problem, we're given the percentages of the elements involved, but we're given them in percent, not grams, and certainly not moles. So the easiest way to approach this problem is to assume that you've got 100 grams. Okay, just make the assumption you've got 100 grams of the sample and convert the percentages to grams. This will get us started. So for example, 6.64% lithium, if you've got 100 grams, is the equivalent of 6.64 grams. 1.92% hydrogen, if you've got 100 grams, is 1.92 grams of hydrogen. 29.8% phosphorus is 29.8 grams of phosphorus, and 61.6% oxygen is 61.6 grams of oxygen if you've got 100 grams. So we'll just make that assumption. Can I make that assumption? Sure I can, right? I can make the assumption that I've started with 100 grams. And by the way, it wouldn't be smart for me to start with something silly like 68.4 grams because I'd have to do the math. This makes it easier. If I start with 100 grams, it makes it easy to convert from percent to grams. Now we need to convert those to moles. So 6.64 grams of lithium is how many moles of lithium? Well, I do the conversion, grams to moles, 6.94 grams of lithium per 1 mole. I just got that from the periodic table. And now this and this are going to cancel. I'm going to be left with moles of lithium. 0.96 moles of lithium then is the equivalent of 6.64 grams of lithium. 1.92, by the same technique, grams is going to cancel with grams, and I'm going to be left with moles of hydrogen, just like that, 1.9 moles hydrogen. So 1.92 grams of hydrogen is 1.9 moles of hydrogen, and I'll just continue to do that for all 4 of these elements. So I ended up with 0.96 moles of phosphorus and 3.85 moles of oxygen. So what have I done? I converted from percent to grams. That was easy because I assumed a 100-gram sample. And then I went on to determine the number of moles that represented because of the fact that I was able to, from the periodic table, learn the number of moles per gram for each of the 4 elements. That gave me the number of moles of each of these elements. Again, 0.96 moles of lithium, 1.9 moles of hydrogen, 0.96 moles of phosphorus, and 3.85 moles of oxygen. Okay? Now, what are we going to do now? What we're going to do is we want to determine the simplest whole number ratio. To determine the simplest whole number ratio, we're going to divide these values by the smallest of the values, which is the 0.96. Of the 4 values, 0.96 moles is the smallest. So we'll divide 0.96 by 0.96 and we get 1. 1.9 divided by 0.96, we get about 2. 0.96 divided by 0.96, again 1. And 3.85 divided by 0.96, about 4. So the mole to mole to mole to mole ratio then is 1 to 2 to 1 to 4. That's the simplest whole number ratio, right? From these molar ratios, we obtain the empirical formula. The ratio of lithium to hydrogen to phosphorus to oxygen, again, is 1 to 2 to 1 to 4. Therefore, the empirical formula would be this. Li, no need for the 1, H2, P for phosphorus, no need for the 1, and then 4. And that's it. That's my answer. Okay? That's the empirical formula given percentages by mass of the elements that are involved. All right? Okay, I hope that makes sense. Now, this problem, example number 4, allows us to use the molecular weight to calculate the molecular formula once we know the empirical formula. So let's take a look at this problem. It says a compound contains 49.3% carbon, 6.85% oxygen, 43.8% oxygen, 6.85% hydrogen, 43.8% oxygen, and has a molecular weight of approximately 145 grams per mole. So the whole thing weighs 145 grams per mole. And they want to know what the molecular formula is this time. So last time we determined the empirical formula. This time we want to determine what the molecular formula, the true formula is, right? So here's how we're going to do it. This problem requires that we not only obtain the empirical formula, but we know the molecular weight to obtain the molecular formula as well. All right? We know the molecular weight, the mass of 1 mole of that. So start by using the same method as the previous problem to obtain the formula, the molecular formula. Okay? Right? Begin by converting percentages to grams. You know what? I'm sorry, this is a typo. This should be empirical formula. Let's change that. We want to determine the empirical formula. Okay? There we go. So begin by converting percentages to grams, right? Now, we've got 49.3% carbon. That's 49.3 grams if we've got 100 grams of carbon. 6.85% hydrogen. That's 6.85 grams if we've got 100 grams. And 43.8% oxygen is 43.8 grams of oxygen, okay? Next, convert grams to moles. Just like we did before, we're going to convert grams to moles. So here it is. 49.3 grams of carbon by this dimensional analysis is going to yield for us 4.10 moles of carbon. I just got these numbers right off the periodic table. Grams cancel away off the periodic table, 1.01 grams per mole, and I get 6.78 moles of hydrogen. And this time I've got 43.8 grams of oxygen becoming 16 grams of oxygen. That's 2.74 moles of oxygen. You remember what the next step was? This got canceled with this. We'd look to see which is the least of these 3. It's this one right here, the 2.74. And we're going to divide everything by that 2.74, right? And when we do, we get 1.5, 2.5, and 1. Now we've got a little problem here. We've got a problem in that we've got fractions. How do we deal with that? Well, to get rid of these fractions, we're going to multiply everything by 2, right? We're going to multiply everything by 2. That's going to help us remove these fractions. The ratio becomes 3. That's 1.5 times 2 is 3. 5, 2.5 times 2 is 5, to 2. 1 times 2 is 2. Carbon, hydrogen, and oxygen respectively. So the empirical formula then is this right here. It's C3H5O2. C3H5O2. But wait, we're not done. We've been asked for the molecular formula, right? We want to know the molecular formula. So the molar mass of the empirical formula is this. We're going to add up those percentages, and when we do that, we get 3 times 12.01, 5 times 1.01, and 2 times 16.0. This number right here is the molar mass, right? So for carbon, hydrogen, and oxygen respectively, it was these right here. And it's a ratio of 3 to 5 to 2. So when I add those up, I get 73.08. Now the molar mass of the molecular formula is given to me. I'm told that it's 145 grams per mole. Now this is very close to twice the calculated molar mass of the empirical formula. So the molecular formula must be twice the empirical formula. So we'll take the empirical formula and double everything. And instead of C3H5O2, we're going to get this number, or this molecular formula, right? C6H10O4. All right? So a little bit more involved on this one because of the fact that we're being asked now for the molecular formula on this one given the molar mass. But it wasn't hard. It's basically the same thing. All right, let's move on. Let's take a look at this example. Example number 5 says this. Boron forms an extensive series of hydrides. Now, don't panic here, okay? Don't panic. We're going to learn in the problem what a hydride is. It says if you isolate a new hydride that is 81.1% boron, a possible molecular formula of the compound is what? This is A, B, C, or D. All right. Now we're going to need to think our way through this problem. All right. We're going to have to think our way through because it's not quite as straightforward as the previous problems. So the options are B2H6, B4H10, B3H9, or B10H14. How would we approach this problem? Well, let's start with the percentages. We know that we've got 81.1% boron. Well, what percent of it is hydrogen? Well, just do a subtraction. A hydride, apparently, from the answers, looks like it's just boron with hydrogen, right? So there's only 2 elements involved, boron and hydrogen. So to determine the percentage of hydrogen, just subtract 100% minus 81.81%. We get this number, 18.9% hydrogen. So now we know the percentages of boron and hydrogen, 81.1 and 18.9 respectively. Again, let's assume we've got a 100-gram sample like we've been doing in the past of the hydride, and this means that 81.1 grams of boron and 18.9 grams of hydrogen are present. So what's the mole ratio of boron to hydrogen? The mole ratio. Well, let's convert those to moles. These are grams now. Let's go take them to moles. By the exact same technique, the dimensional analysis that we looked at before. Remember that grams and grams are going to go away. I got that right off the periodic table, 10.81 grams per mole. And again, for hydrogen, that's going to come off the periodic table. And here's what I get. 7.50 and 18.57. That's moles of boron and moles of hydrogen respectively. Next, we'll determine the ratio by dividing by the smaller of the two, which is 7.50. So we get 1 and we get 2.49 or about 2.5 respectively. So the ratio of boron to hydrogen then is 1 to 2.5. How do we get rid of that fraction? You can't have fractions, so double both of them. 1 becomes 2, 2.5 becomes 5, is the ratio of boron to hydrogen in the empirical formula. It's a 2 to 5 ratio. So what we're going to do then is the empirical formula now we know is B2H5, so the molecular formula can be any ratio of this one. If we knew the molar mass, we could determine the molecular formula, but we don't, right? All we know are the possibilities. The answer must be B, B4H10, because that's the only one that is a multiple of B2H5. So that will be our answer, B. Folks, that'll do it for this one. I'll see you in the next one. Thanks. Bye-bye.